Hello everyone, today I am back with my presentation. Today's lecture is on memory management strategies. My name is Shivansh Kumar, a BSc CS student. So what will we basically learn today? Background swapping, contiguous memory allocation, segmentation and paging. So what are the subtopics covered in background? The first topic on our index, uh, address binding, dynamic loading, dynamic linking and physical versus logical memory space. Address binding basically is the process of mapping from one address space to another address space. Logical address is the address generated by CPU and the physical address refers to the location in a memory unit. So address binding is of three types: compile time, load time and execution time. Compiler time, if the compiler is responsible for performing address binding, then it is called compile time address binding. Load time, it will be done after loading the program into memory, and execution time, it will be postponed even after loading the program into memory. The program will be kept on changing the locations on memory unit in the time of program execution. The dynamic type of address binding done by the processor at the time of program execution. Load time, this type of address binding will be done by the OS memory manager, that is loader. Now comes the logical versus physical address space. The basic difference between logical and physical address is that logical address is generated by CPU and the physical address is physical location present in memory. Dynamic loading is a routine of program which is not loaded until the program calls it. All routines should be contained on the disk in the relocatable load format. The main program will be loaded into the memory and will be executed. Dynamic loading also provides better memory space utilization. Dynamic linking is a method that helps the operating system to collect and combine various modules of code and data information into a single executable file, that is .exe file. The file will be loaded into the memory and executed. Operating system can link system level libraries or the input libraries into a program that combine the libraries at load time. In dynamic linking method, libraries are linked at execution time, so program code can remain small. Swapping refers to a mechanism in which a process is swapped temporarily out of main memory to secondary storage and make the memory available for other process. This helps in running multiple and big processes in parallel, and that's the reason swapping is also known as technique for memory compaction. This allows multiprocessing and it becomes sometimes time saving also, because the program which are not in the more priority are stopped, and the program which are needed at that time, means which are the more at more priority at the time are given space which can be get executed. So now as you can see in the diagram, there is main memory and secondary memory. There are several processes running in secondary memory as well as main memory. So in main memory, the process which is not in priority or does not need to be executed at that time is swapped out in the secondary memory which runs at that place, and the processes and which are in more priority at that time are taken from secondary memory to main memory and that get executed first. The total time taken by swapping process is the sum of time taken by the entire process to move to secondary disk and then to copy the process back to memory, as well as the time process takes to regain main memory. Now comes the turn for memory allocations. The topics which we'll cover in memory allocation are memory protection, memory allocation and fragmentation. So what is memory protection? This basically means when you need to protect your system from third party applications or third party software which may harm the other processes. This is known as memory protection. Now comes memory allocation. Memory allocation is a process by which computer programs are assigned memory or space. Here main memory is divided into two partitions: low memory. Operating system resides in this type of memory. High memory, user processes or third party application softwares are held in high memory. Now comes the topic for partition allocation. First fit, best fit, worst fit. First fit. In this type fit, the partition is allocated which is the first sufficient block from the beginning of the main memory. Worst fit, it allocates the process to the partition which is the largest sufficient freely available partition in the main memory. Best fit, it allocates the process to the partition that is first smallest partition among the free partitions. There are algorithms for all the three partition allocation strategies. You may pause the video and read them to get it more. Now we reach the third topic of memory allocation. Fragmentation means dividing the memory into several small blocks for the process execution. Suppose an process needs 10 MB of memory to get executed. A 10 MB block will be created, which will be kept separate in the memory. After the process is executed, the block does not get mixed into the main memory. Either it is separate block kept aside, due to which the memory gets booked and the memory does not get free for the other process to get executed, due to which there are several problems like lagging of operating system and etc. There are two types of fragmentation: external fragmentation and internal fragmentation. There are methods for both to reduce them. External fragmentation can be reduced by rearranging memory contents to place all primary memory together in a single block. And internal fragmentation can be reduced by assigning the smallest partition, which is still good enough to carry other processes. Means the blocks which are already created should be assigned to the process which need the same amount of memory. Now we reach a final topic: segmentation. Segmentation is a memory management technique in which memory is divided into the variable size parts. Each part is known as a segment, which can be allocated to a process. The details about each segment are stored in a table known as segment table, and the segment table is stored in any of the blocks or segments. Segment table contains mainly information about segment, which is base, the address of the segment, limit, the length of the segment. Translation of logical address to physical address through segment table. CPU generates a logical address which contains two parts: segment number, offset. The segment number is mapped to the segment table. The limit of the respective segment is compared with the offset. If the offset is less than the limit, then the address is valid, otherwise it throws an error. In case of the valid address, the base address of the segment is added to the offset to get the physical address of actual word in the main memory. So now comes the turn for the final topic: paging. Paging is a memory management scheme that eliminates the need for contiguous allocation of physical memory. This scheme permits the physical address space of a process to be non-contiguous. Now let's study our paging technique. The mapping from virtual to physical address is done by the memory management unit MMU, which is hardware device, and the mapping is known as paging technique. The physical address space is conceptually divided into a number of fixed size blocks called frames. The logical address space is also split into fixed size blocks called pages, where page size is equal to frame size. Address generated by CPU is divided into page number P, number of bits required to represent the pages in logical address, page offset D, number of bits required to represent particular word in a page. Physical address is divided into frame number F, number of bits required to represent the frame, frame offset D, number of bits required to represent particular word in a frame, or frame size of physical entry. The hardware implementation of page table can be done by using dedicated register, but the usage of register for the page table is satisfactory only if the page table is small. If the page table contains large number of entries, then we can use TLB. The TLB is associative high-speed memory. Each TLB consists of two parts: tag and value. When this memory is used, then an item is compared with all tags simultaneously. If the item is found, then the corresponding value is returned. As you can see in the diagram, the CPU generates the logical address where the P page number is checked. If it is in cache, then it goes to TLB. If it is not there, then it goes to page table. Then if it goes to TLB, the TLB gets hit, which gets stored into F frame number. Even if the TLB gets missed, it is stored in F frame number, where F and D combine to make the physical address. Here is the formula given for calculating effective access time, which is equal to M for page table and M for particular page in page table. where m stands for mean memory access time, where effective access time is equals to hit ratio into c plus m plus miss ratio into c plus m. So we are with our today's presentation. Hope you got everything I tried to explain you. Meet you next time. Bye bye.